Now our special guest speaker, Kirk Pepperdine. That's his Twitter handle, and he's a principal engineer at Microsoft. And in fact, before that, he's a co-founder of jClarity, which actually got acquired by Microsoft back in 2019. So now he's at Microsoft, and he has over 20 years of very deep experience in Java performance tuning. And he's the author of the original Java performance tuning workshop. He's also a Java champion since 2006. He's got the thought leadership in Java performance. And he has been named numerous times as Java 1 rock star. He's also a co-founder of jCrete, and so that's the Unconference, an open space conference on an island in the Mediterranean Sea, and that's what the website says, so I copy it in here to let you know. And then he's also an ardent supporter of the Java community. So with that, we welcome you again, Kirk. I'm really happy that you're here. So the mic is all yours now. So.
Oh, thank you, Mary. I mean, it's yeah. I was looking at the lineup of speakers you have coming in, like Charlie Hunt. He's local to you too, right? So
that is correct. Yeah. He's in Liberty.
That's a legendary speaker. So the garbage cooking talk.
We have been so blessed, I guess.
I mean, really good lineup there. It's amazing. You guys just keep rolling them in. Okay, so I should share screens and stuff like that, I guess, to get going here and everything. Yeah. So I think it's been a while since I've been in Chicago, actually.
Yeah.
And the last time I was there, we did have the opportunity to speak. At that time, we did a whole Q&A, I think, if you remember, right?
Yeah.
It was just all Q&A at that time.
That's right.
And normally in the last number of years, I've been spending a lot of time talking about memory because it's just a topic that we just kept running into over and over and over and over and over again, and it was just something that I think we just wanted to help people with to understand, because it was not only that we're just talking about memory a lot, it's that we were running into the problems and we're finding that people weren't recognizing the problems that they were having with memory and how it's impacting the performance of their application. And because of that, I just did this whole series of talks on memory that pointed not specifically at the garbage collector, but at churn and the cost of churn and how you get churn and why churn happens. So just a whole bunch of topics like that. And so this one is kind of different because it has nothing to do with memory churn or anything, but it's one of these problems that we see emerging in the industry. I mean, it's always been around and you see instances of it, but I think it's become more prevalent in the last few years, and really that is I think a consequence of some of the more modern architectural styles that we're engaged in. So and it's also, I think, a problem that a lot of people don't really recognize either. Because of that, it's just one of these things that we figured, okay, well, maybe it's time to start, I was getting bored of talking about memory, so let's talk about something else. So here we are and everything. I think we have mics open, so we should take questions on the fly, I think. So if you want to interrupt and ask a question, feel free to interject or comment or question as we go through here. Okay, so Mary did a much better job of this than I did. Normally I say, go look at Google and we're done, right? So that's pretty much for that. So I wanted to, it was a number of years ago I read this book, and I thought it was really cool. Actually, I still have it on my shelf here, so go get it. Should have brought it down beforehand, but it's not there. Now I'm back. This one, can you see that? Yeah, there we go. And it's like anti-patterns. It's really cool because it came out just shortly after. I got some weird things in here with what's the date on it? I don't know. It doesn't really matter. It was like it came out just after the Gang of Four book came out, and a little while after, about a year after and it was really focused on anti-patterns. And of course, at that time, design patterns were really being popularized, and there's, so many people who do really excellent talks on design patterns. I don't even bother to touch it. Vinkat's done a lot of it. Heinz has done a lot of it. There's just so many people talking about it, and they do really good job. So, but I just want to touch on a design pattern and then try to contrast that with an anti-pattern. So if we look at this, you can see with the design pattern, we have some problem. There's some context within that we're trying to solve this problem in, and there's other forces that are on us that make us come up with some solution to this particular problem. And of course, we get some benefits and we get some consequences from our solutions. And the design patterns really come out of, do we see this happening frequently over and over and over again? And if we do, then, the design patterns sort of formalize this into a language. I think we call it plop. And that allows us to come up with some way of describing our designs concisely to other engineers. And, that's really the purpose of the design patterns, which I think we're all familiar with. And this is really popularized again by the book written by the Gang of Four, and there's subsequent books that I think were just like catalogs and catalogs of different things, of different design patterns. Pretty much the only book I was involved with was Enterprise Integration Patterns, Gregor Hope and Bobby Wolf, and where they did a community effort to document a lot of patterns for integrating applications. So we have numerous observations of the solution, and that out of that follows a design pattern, right? So that's we can read the text here on the slide, but boringly it says reusable template for a solution to a commonly occurring problem. And we have a language now for describing, factory, singleton, adapter, command. These are all patterns I think that we're very familiar with. And what we want to talk about here is like anti-patterns. So, so the question is like, so we have these things that we do, and we know if we do them, we end up generally with good results. How do we catalog the things that we do that don't lead to good results? And that's really where the idea of anti-patterns came out. And in particular, what I was interested in were the performance anti-patterns. So those things that we do and they're commonly occurring. So this is a design problem, right? And when we follow these particular coding patterns, we tend to get ourselves into trouble. So they lead to negative consequences. And, the anti-pattern template is very similar to the pattern template in the sense that you have all the same issues that you have when you have patterns. So this is something that you're going to commonly see, and from that you're going to basically draw out of it saying like, don't do this because this is going to lead to something that we don't really want to, lead us to a place where we don't really want to end up. And more importantly, it's going to say, rather than doing this, why don't you try doing that? So we'll give us an anti-pattern solution, which is generally a pattern. And that's going to be like a refactored solution of your anti-pattern. And, hopefully those will bring us the benefits that we want. And so with this in mind, I really wanted to talk about what I would call, what's been cataloged as the revolving door anti-pattern. And I thought for a little bit of fun, I thought, okay, well, let's try to figure out, okay, so where did the term revolving door actually come from? And it turns out it's invented by this Theophilus Van Kannel guy in 1888. And, there was a whole bunch, he never really said, well, how or why he came up with this thing called the revolving door, which I guess we're all familiar with. And the fun one I saw was that it was to prevent horses from entering the building, right? So, it turns out that's really kind of false. And there's a little bit of interesting history behind the guy if you want to go read about it. But Theophilus didn't like the social etiquette of doors. So he's trying to figure out a way that he didn't have to be obliged to hold doors open for women, which was, yeah, anyways. So he came up with this revolving door. And of course, now there's an etiquette for using that with women, but whatever. Okay, and it turns out there's some advantages to using the revolving door. It's fantastic for energy conservation. They say that buildings that go completely to revolving doors have huge energy savings, especially when you get into periods of extremely hot or extremely cold temperatures. And the other benefit is it does help moderate foot traffic. So you can see with this, that looks like I got that from I don't know. Anyways, from a mall, and you see people coming in and out. They can choose whichever half of the revolving door they need to use to get through. So it's kind of nice that way. So they actually do have a lot of benefits for using them. So that doesn't look like an antipattern. So how do we actually turn this into an antipattern? Well, if we look at the name revolving door, how do we get into this situation? Well, the intent is that we need to drag data or perform calculations that cause us to drag data over inexpensive barriers. And in the case that we're looking at here, that's going to trigger a voluntary context switch. And so now I guess we should talk about the difference between a voluntary and involuntary context switch. So if you think about thread scheduling, and really this is going to be a talk about that's going to be somewhat rooted in thread scheduling, what's happening is that your thread is going to get a time quantum after which it's going to be interrupted and it's going to be punted out of the CPU, and then another thread will come in and make some forward progress, and the cycle continues. So if it's used its entire time quantum and it gets punted out, then that's known as an involuntary context switch. A voluntary context switch is when we're in a situation where I do something and all of a sudden I become blocked. So instead of, not allowing the CPU to make forward progress with something else, I'm going to get punted out at that point, and that something else will come in and it will hopefully make forward progress. So it's a way of trying to get better sharing with the CPU. So when this antipattern was first realized, it was way back in the days of EJB, if anyone remembers that. So Enterprise Java Beans. I guess, I don't know, it's sort of now evolved into microprofile and all of those wonderful things. But you can see that, with the EJB, initially, the client-side APIs were not serializable, and therefore to do any work, you had two ways of doing it. You can normalize the work on the server, or you could drag all the data over to the client. And when you dragged all of the data over to the client, you basically do this one element at a time, right? So I go get X, get Y, get Z, do my three-dimensional calculation, and basically throw things away, right? But that's all network calls, right? It's like 3 network calls to do the get Y, get X, get Z. Right. And if you think about it, it's like every time I go to the network, I'm going down this really long, expensive path to get to my data. So these calculations are engaging what I call these high latency calls. And if you're doing that frequently enough, then you just have like huge numbers of these high latency calls. So known uses for this anti-pattern, most famously, I think it's called ripple loading when you're using Hibernate. So that's when you're trying to do a join in memory in the Java space instead of delegating the join to the database, right? So it's a very common thing when you have relationships that you're trying to remap in your application. And more recently, we see this in microservices. And I guess the other incantation of this is what we call functions. But all functions come with their own sets of, are we seriously doing this type moments? I guess you could call them that. So the obvious solution to this, and we did this with EJBs, is we came up with this nice pattern, which is called DTO, data transfer objects. And I imagine many of you are familiar with this particular object. We just create this serializable thing, and we just dump all of the data we want into it, and we make one call, and we get the DTO. After that, what happened was that the client side, or sort of the server side component of the EJB, became serializable. So if you said, get data from the in the EJB sense, what it would do is we just serialize the whole thing and just basically drag it over, so you didn't have to have these intermediate DTO thing that you had to deal with. As you can imagine, that's a lot of extra serialization. And I think, when I was talking actually to Bobby Wolf about DTO and the use of DTO, it was kind of, we thought the pattern now actually was being abused to the point where DTO is becoming an anti-pattern because people were using it when they didn't need to. And because of that, what we saw in systems was marshalling protocols on top of a marshalling protocol, on top of a marshalling protocol. And then after you have marshaled all these things and flatten them, you run them across the wire, which is fairly efficient. And then you do this very inefficient, like unmarshalling, unmarshal on top of unmarshal on the other side. And then people said, oh, this is going to provide us decoupling because, obviously, I don't have this direct connection between these two things. It's, yeah, sorry, that doesn't work out. You actually do. You have this data transfer object that's in between that's actually coupling your project. So it might not be so explicit. It actually becomes implicit. And that causes its own issues. So eventually we just decide that DTO is an anti-pattern unless it's used in a very specific number of cases. Yeah, so it's kind of fun. So I think this is best seen by looking at a couple of case studies, and so I just picked on two. The first one is actually interesting. I really can't identify it, but it's interesting because it's ongoing, and we have some interesting things that might fall out of it. Right. So case study one, service is performing poorly. Wow, that's an opening, right? I mean, otherwise, why am I involved? Symptoms, client stalls and suffers from stability issues. Very common when you see things misperforming. Then we often see many stability issues falling out of that. So the action taken was, well, it's a Java application. Every problem we have with Java has to do with memory. So what are we going to do? We're going to increase the memory footprint. Right? What else would you do? No, I don't. I no clue, but that's what I would do. Okay, so we make the footprint bigger. And voila, it works. We can improve performance and stability. Everything is really wonderful, except for now our cost of goods sold, or the cost of hosting the service, is now skyrocketed because we have bigger machines, because we have a bigger memory footprint. So so that's an issue. Okay, so now we're trying to figure out, okay, what's going on here, right? So now we get into the stuff that we're not told, right? Because everyone, you always get into the situation. It's like people say, hey, we have this issue, and then there's a whole bunch of things you're not told that you just discover afterwards. Like the most interesting case was my last engagement before joining Microsoft. I went to a place and they said, we have this large distributed database query thing. It takes a long time to do queries, and this thing stalls out and crashes, and we think that it's having to do with out-of-memory errors. Right. So and they weren't able to send me any data prior to, and we got in there and I looked at it saying like, at first I was trying to set up for, heap dump analysis, try to figure out, what's happening that way. And we get in, and what we notice is that they're making calls to system GC every, I don't know, it worked out to every 30 seconds or something ridiculous like that. Of course, eventually that interfered with the heartbeat mechanism, which caused JVMs to drop out of the cluster. And apparently this was a vendor recommended setting. So it took 3 days of meetings to get them to turn it off. It's really fun. Okay, anyways, so you get these stability issues that come, and you're not told everything. So in this case, what were we not told? Well, increasing the memory footprint meant that they had fewer servers per machine, right? So in that case, that's why the service required many more servers, which is why, and they had bigger servers, and so, that's where the costs went up. So the first thing I did was looked at it and says, okay, let's just take a look and see what's happening in the system. So we got this output from just VMstat. It's it's a OS level tool, Linux, gives you a basket of kernel performance counters. And I don't really want to go through the whole basket here because that's not really that important. And maybe many of you are familiar with the tool. But, actually, this is a fun one. Since we're at a jug meeting, we try to make it fun. There's the numbers. If anyone's experienced it or has looked at these things in the past, the question I have for you is, can you see anything outstanding in this particular data set? I'll stop for a minute to see if anyone can look at it and come up with something quickly. Now this is a busy server. Has anyone got anything or nothing? Nothing outstanding, right? Yeah, that's okay. If you don't see what's going on here. Did I hear someone say something? No. Okay. Well, let's just trundle forward and see what's going on here. Yeah. So the three important columns, as it turns out, in this analysis are right here. That's our CPU breakout, where it's counting, well, effectively percentage of time in each of these particular states. And the three important columns in this case are the user time, the kernel time, that's the SY column, or the idle time, the black column, right? The wait time and the steal time are all 0 here. So it's useful information in context, in the overall context, but for this particular problem, it's not, right? So if we look at these particular numbers, we can start doing some calculations with them. So if we look at the user time, it's approximately, eyeball 5%, give it that. Then we look at the system time, that's approximately 25%. So if we look at the ratio of user time to system time, that's 20%. Now, what I have is a magic number. My magic number is 10%. And what the 10% says is that that's the acceptable threshold. That's a threshold that I'm willing to accept in terms of ratio of application usage of the CPU and kernel usage of the CPU. And there's a number of different reasons why this 10% number seems to be okay. Well, first, this 10% number is very Java specific. But what we see is that the operating system has a lot of serialization in it. There's a lot of things where you're naturally serialized. And as a consequence, you're going to get hit very heavily by Amdahl's law, just because of that serialization pressure. And you're going to get hit very quickly. And that means that your application's pressure on the kernel is going to be your primary bottleneck in your application. And in this case, we see that 20% is much greater than 10%. And therefore, what I'm looking for is that application operating system interaction. So the question in this case is like, what is causing this excessive pressure on the OS given this low level of user activity? Yeah. And we can go and look at the other counters, and they can help us fill in some of the picture here. So at this point, I might switch to another tool set. But before I do that, I'm going to look at, try to get an idea of what's going on here. So the first thing I'm going to look at is the, let's see if I can get to another slide. Yeah, the runnable queue. And you can see that here we have lots of idle time, and we have threads that could be scheduled and they're not scheduled. We have a little bit of blocking going on, but not enough to be significant, right? To be seemingly a significant problem. But the problem is we got tons of idle and we have runnable. And, that sort of hints that we have a scheduling problem. And in fact, if we look at the context switching rates, you can see that they're pretty high. They're, well, I said approximately 70,000, but I think if I was to be realistic here, they're between 70 and 80, closer to 80,000 context switches per second, right? And that means that scheduling is a problem. And yeah, it's really a problem. Now, the fun thing about all of this is that now what we're going to do is we're going to shut down all the clients, and we think like, okay, well, since the clients are not putting pressure on the server, then obviously the context switching rate should come down, right? Sure, seems reasonable, except for in this case, look at that, context switching rates increase. They're now consistently above 80,000 context switches per second, right? Which sort of leaves you in, this particular state. Like, what? Okay, what's going on here? Right. So let's put this one aside for a second, and let's go to case study number 2. In case study number 2, service is performing poorly. Okay. That sounds very similar to the previous one, right? And every other one. Symptoms: clients wait for minutes for a simple web access. So we have an in-house application that does scheduling. There's probably about no more than a dozen users on it at a time, and they're waiting minutes just to get data back from any of their queries. Right, so action taken in is, so what are they doing about it? Probably nothing. Yeah. Consequence here is really that this project is canceled. So we're called in to try to see if we can revive the project so that it's no longer canceled. So we look at this with the initial investigation. We see this is just a really simple 3-tier web application. So browser to web app to database. As I said, there's a very low user count on it. And we start asking questions around. I started asking questions like to different people. It's like, is the database performing well? And yeah, there's no database issues. We're clearing queries in the sub-millisecond range. The network, lightly saturated, no issues with the network, right? So in this particular case, you have to look at the problem and say, okay, the service providers are serving, and they're providing a good service. So we think of the network as being a service provider. We think of the database as being a service provider. They are performing, well. There's no issues from that end, which means that you have to look at the service consumers to see, okay, now how is it that we are consuming the service? And this is why we like to look at both sides of the picture, because then I can compare and contrast the service provider performance with the service consumer performance, and then you can get some deep hints as to what's going on. So this is running in a Windows system. The other one was Linux, just to show you that these are equal opportunity performance killers. Here we have a breakdown, kernel user time, and the numbers are jumping all over the place here, as you can see, but we can do some estimates. Oh, by the way, the one on the bottom that you can't really read, sorry about the bad screenshot, but this is real screenshot off real system, and it hasn't been graphically enhanced. But you can see memory here is not an issue. The memory utilization is very flat, so we don't have any memory issues here. But even with this like crude level of information, you actually have a lot more than you think, in the sense that if we look at the calculation for this particular situation, we can see that, I'm going to estimate the user time is about 20%, and the kernel time is, say about 50%, something like that. So we get an approximately 40%. So you can see that now we're well above that 10% threshold. So in this case, there is an excessive amount of pressure on the operating system itself, right? So it's likely that this pressure is your primary bottleneck in your system, and what we want to do is try to discover, what are we doing in the application that's causing all this pressure on the kernel, right? So, and that's really the question that we have here. What do case number 1 and case number 2 have in common? And the answer is that we have a high kernel to user ratio, 40% in one case and 20% in the other case. So it's all pretty high. And what we're hinting at, especially with the Linux counters, is that we have many small tasks, right? And the question is, okay, so if we have these many small tasks, why is that putting all this pressure on the kernel? And as it turns out, we then have to ask the question, okay, what is the kernel being asked to do? And how much does it cost to do that? And in this case, you can look at the context switching rates, and you see they're extremely high. So in effect, what I've done is I've hyperactivated the thread scheduler. So it's now hyperactive, and that's the thing that's consuming all the kernel time. Now, when you think about thread scheduling, which we're going to get into very shortly, you're going to understand that there's a lot of downstream consequences of hyperactivating your thread scheduler, and none of them are good. Oh yeah, 2 questions. Why is 10% considered a threshold? Yeah, so much of the kernel work serializes the workflows. Either queues or serializes via locks, via schedulers, work queues. There's all kinds of different ways that we ensure that we have singular use of individual pieces of hardware. Right. So if you look at the thread scheduler mechanics, what you recognize is that there's been a lot of work done in this area, and there's some interesting studies. I think I point to a couple of them here. There's one done by the Polytechnical in Paris, and there's another one that's the UBC in British Columbia, University of British Columbia in Vancouver. But they all come down to the conclusion that our current way of thread scheduling is leaving a lot of idle cycles. And if you go back to the numbers, we saw that we were getting approximately 60% of our cycles were idle, just consumed by the idle process. So, so what's going on in there, right? So with thread scheduling mechanics, what we're looking at is saying, okay, so I got the CPU and I got a whole bunch of different tasks, and I want to make sure everybody gets some fair share of the task for some unreasonable definition of fair share. It's never really fair, but whatever. And so the thread scheduler is responsible for just taking all of these tasks in the task queue and saying, okay, core, I got all these cores, here's all the tasks, make sure that all the cores are kept busy executing all of these tasks. Now, as it turns out, it's kind of difficult to get into any work stealing mechanisms at this particular level, and and how it's set up is difficult to maintain these queues. So what happens is that we're going to end up with a task queue per core. Okay? And one of the tasks that will be scheduled is the thread scheduler. And it typically will run on core 0. And its job, as I said before, is to load up all the task queues. And then it schedules itself to run. So, so you can see now, all of a sudden, with this particular scheme, you can see that, wow, okay, so I'm running these really short tasks. So how is that going to be managed by the thread scheduler? And the answer is very poorly, right? Because as we divide the CPU between tasks, what we're going to do is we're going to assign a time quantum. Now, in modern versions of Linux, or recent versions of Linux, this time quantum is elastic in the sense that it will adapt itself on a per thread basis, because it will understand that, oh, this thread tends to context quickly, so I'm going to reduce its time quantum, where this thread tends to stay in the processor, so I'm going to increase its time quantum, and hopefully over time these things will stabilize out to some interesting value. But other than that, what we tend to end up with is a lot of involuntary, or a lot of voluntary context switching, right? So when the time quantum expires, the task can be involuntary context switch out, like I described before. And in this case, the rate of context switching is going to be inversely proportional to the time quantum. More importantly, it's predictable. And if it's predictable, that means that I can act. When things become unpredictable, right, as is the case with voluntary context switching, then I'm reacting. And not only is reacting more expensive, it means the thing I'm reacting to has to wait while I'm reacting. And that's the important thing here, because that's the thing that idles you. So if the task blocks or is finished and we voluntarily context switch out, the rate of context switching is going to be inversely proportional to the size of the unit of the work before the task completes or blocks. Yeah, so that's the situation we're left with. So when we get into these increased rates of voluntary context switching, we're going to hyperactivate the thread scheduler, and that's going to heat up the kernel, and it's going to leave cores idle. And it gets even more difficult than that, or more tricky than that, because what happens is that cores will exhaust their task queue, and then they'll just idle. And they'll be idled until the thread scheduler, which is running in core 0 sometime in the future, don't know when, actually refreshes all of their task queues, right? And hence you get all of this idle time. And people see the idle time, they see the bad performance, and they figure, okay, well, I'll just throw more threads at the problem. But as you can see, more threads at the problem actually end up making the problem worse, which means your idle time will go up, your kernel time will probably stabilize, but your user time is going to go down, and your response times are going to go even longer. And I think a way of looking at this is you have to think of the thread scheduler is always in your critical path. It's always there. Okay, and if you're doing context switching, then you're not doing work. And the other thing to think about this, right, it's not just in your critical path. This is a global effect across the piece of hardware, which means that your behavior in one application or one deployed unit is going to affect the performance of everything else running on that piece of hardware. Right. So now let's go back and look at the information we had. So we had a particular context rate at somewhere around 75, 78,000 per second, right, for the first case. And when all the users logged out, all of a sudden the context switching rates jumped to 83,000 per second. And as soon as you see behavior like that, I'm thinking like, okay, well, that seems to be like something to do with Little's law, right? And what Little's law says is if I have a point of serialization in my system, which I know I have, that's called thread scheduling, then the throughput is going to be inversely proportional to the service time. And all of a sudden you're thinking like, wait a second, I have a bunch of threads that are doing some work, okay, and because they're doing work, that means it takes more time, which means I'm going to have lower throughput. And then I have these threads all of a sudden not doing any work, which means they have, which means it takes less time, right? So they're, and we do the inverse of that, means that my transactional rate goes up. So that to me indicates that these threads are always cycling. They're not parked anywhere. What they're doing is they're just spinning. And they're spinning over a lock someplace, right? And if you look at the core component to this particular application, it's Netty. And if you think about how Netty can be configured to work, I mean, that's one of the modes that you might use it to work, especially if you're in an event-driven system. And strangely enough, I mean, my work in Chicago has all been on event-driven systems, but all of those event-driven systems have been single-threaded. And one of the reasons why it is single-threaded is because you start avoiding problems like this when you start introducing threading into your applications. And if you want really, really high throughput, then single thread is actually a much better option. Right. So logout case, a smaller unit of work. The cores burn through the task queue more quickly. It just hyperactivates the thread scheduler even more. Right. And this is an example of what we call a revolving door antipattern, right? In other words, I have something that's just spinning over an expensive resource. In this case, the expensive resource is thread scheduler. Remember, thread scheduler is always in your critical path, which I don't, it's a thought that I don't think many people have when they're looking at code or looking at their system. In case study 2, we had many small calls to a database. Again, this is to perform a join in Java. So this is our ripple loading thing that I spoke to at the beginning. And the database and the network are able to manage these situations, piece of cake to them. They don't even break a sweat, right? They're just humming along really nicely. It's like, give me more, right? But what we have is these, on the client side, we have these threads spinning over the network interface. And they do a small amount of work, and then they context switch out because they got to get a lock to get onto the frame buffer, and all that mechanics down there, how that all works. But as you can see, effectively, we have some point of single threading there, means we give it up, but we have a bunch of threads spinning over that. They do small amounts of work, and all of a sudden our context switching rates go through the roof, and that again hyperactivates our thread scheduler. So again, this is another example of what we call a revolving door antipattern. Yeah. So obviously, the answer to this particular case is like, let's do the join in the database instead of in Java, and then pull the data over. So that's one solution. In the other solution, the other case, we don't really have a good answer to that particular problem yet, because Netty is ingrained into the architecture of the application, but somehow we have to come up with a better solution for that. The interesting hack around for that particular problem was that what we did was we took the app, we did a study in the memory and said, yeah, okay, your heaps are like way oversized. So what we can do is we can reduce the heap size, actually even smaller than they originally had it. And because of that, there was huge performance wins just simply because of that, right? As soon as we got to the smaller heap size, they looked at it and says, "Ooh, we can put like a dozen or so. Uh, uh, we can put a dozen or so JVMs back on this box." And we're going like, "No, you can't do that." I'm sorry, there's something happening here. Oh, jeez. And no, you can't do that. What you need to do is distribute the JVMs across many more machines. So have many smaller machines. And in that way, what happened is that they get a reduced footprint. They get the benefits from that. They have more machines, but they're all smaller, so they're a lot cheaper. And so what the benefit of all that is that eventually they go from being in the red to being in the black again for this particular service, just because of the reduced cost. Right. And the other issue, I guess, in all of this is that hypervisors increase the amount of work that the scheduler has to do, right? Because the hypervisor is advising the thread scheduler as to what to do. So it sort of has to consult with this thing. And you know yourself, like even any task that you're doing, if you're working away and all of a sudden you got to stop and consult with somebody else, it just takes longer, right? And so more work equals longer service times, equals hotter kernel, and also a slower application. So we'll see that hypervisors will have some detrimental effect on this system. Now, I guess it's the type 2 hypervisors are going to be better than the type 1 hypervisors. The original hypervisors would slow our benchmarks down by a factor of 2, at least the ones that stress the thread schedulers. Right. So the conclusion of all of this is like the revolving door anti-patterns of work will inflate voluntary context switching rates, and it's going to place the thread scheduler into a react mode that's going to idle cores, heat up the kernel, just all the things that we've been talking about. Really, the solution here is to bulk up the unit of work on the back end somehow, right? So in the first case, what we hope for is that the system wouldn't be processing individual events, but chunks of events, as an example. For the second case, it was to not do that get type behavior, but again, do the work where it was the most efficient to do it and made sense to do it. In other words, doing the table join in the database and then pulling the data across in a single chunk was the solution to that particular problem. And your solution is really going to depend on the situation that you're in. But the idea here is recognize where that expensive barrier is and make sure that you don't transition it as frequently as you are currently transiting it. So one of the ideas we have for the first project is Project Loom. So I don't know how many people here are very familiar with Project Loom, but there's a URL so you can go and look it up. So Project Loom, I just grabbed that directly from their website. So I did a Mary on this one. And as you can see, it's what they're looking to do is add virtual threads, or what they call fibers. And they want these fibers to support continuations. And so if you look at synchronous calls, what happens is that I'm going to make a call and block. And when I block, then I do the voluntary context switch. So with if I drop into a continuation, that means that thread can still be active doing other things. And effectively, the context switch is going to happen at the fiber level and not at the hardware thread level or at the virtual thread level, right? And it's, so there's some cost to that, obviously, because you're still doing a context switch. And so that's not free. But potentially that's a cheaper context switch than a full context switch in the system. I guess they're also working on tail call elimination, but that's a side conversation to this whole thing. So if you think about what a continuation is, so just grab this randomly this definition because it seems to work, right? Continuation is a data structure that represents the computation, the state of the computational process at some point in time. So more importantly, this is a data structure, meaning that represents state. That's basically in CPU terms, we call this an exchange packet, which is the state of all of the registers, which means that when I context switch out, I can just I can take that state, save it someplace, and later on, context switch that that state back in, and then continue the computation as if it hadn't been interrupted, right? More importantly, what this means is that instead of using hundreds or thousands of threads, which have very detrimental effects on the performance of your application, what you're going to see is that you have one thread and it's going to stay there in the CPU a much longer time. And that in some of the benchmarking that we've done for this, we see that we're able to get much higher throughput in our systems. Where you get far fewer threads. So if you think of safe pointing behavior in the JVM, that all happens much quicker. There's just less resistance in general when you have fewer threads. And the side effect is that these fibers should lighten the load on the thread scheduler. In other words, the way that this particular application is managing events, if we switch it to fibers, I expect what it's going to do is instead of we can reduce the number of threads to manage all of the events that are coming in at the rate they're coming in, and we should also drop the thread scheduling, the context switching rates significantly. How much, I'm not sure, but I would expect a factor of 4 anyway. So which means that aside from the global improvements in performance and stability, we should be able to service many more virtual machines per unit of hardware, and I think that that's going to further reduce the cost of operating this particular service. And with that, that's pretty much all I have to say. So we go to questions. That's the Twitter handle I prefer. Not the one that Mary posted earlier, or if you have, you can send questions to me at this particular email address. Right. And I will pass the screen back to you, Mary.
Oh, can leave this on
And
too.
I guess how do we manage questions now?
Yeah, so I think that we can invite anyone, if anyone has any questions, please turn on your camera or turn on your audio and ask the questions directly. Or if you don't want to talk or show your face, and you can always type your questions on the chat dialogue there as well.
Okay. I'm
So
going to
yeah,
stop sharing my screen so I can see everything that's going on here, because I wasn't able to see questions and I didn't hear questions. So
that's right. I
have a
see.
question.
yes.
Please do.
What is your experience with pinning a specific process to a specific core using Linux task set?
Do I have experience with that? Yes.
No. My question was, I thought that you had that experience, but kind of, what to watch for, how to use it in a proper way. Was it good for when to avoid it? That type of experience I meant, not just if you had of that.
Yeah, I think if you have the thread, if you like in the single thread system case, we definitely wanted to pin that thread to a single core, because generally the way the thread schedules work is they will round robin the task onto different cores, right? And you'll see that if you run a single threaded application on your system, it'll bounce through core 0, core 1, core 2, core 3. And obviously you'll turn the hyper-threading off in those cases, right? And you'll generally see a fairly even utilization of all 4 cores. Obviously this comes with some consequences, because that means that you're going to miss out on cache alignment, right? So every time you context switch to a different core, then of course you're going to have to realign the caches to to whatever the thread is doing. So that's okay when you go from core 0 to core 1, but as soon as you switch to core 2, then of course you're on a different L1, L2 mix, right? Which means that, the cost of the fetch is different. So generally when we get into that level of performance tuning, one, you need to have a problem that really warrants it, I think, the extra headache of doing all of this. And two, the single-threaded case was really nice because it meant that we prevented this skipping behavior, which meant that the caches were always going to be aligned with the thread that was managing the events that were incoming. So that's one case when I use it. To be honest, I haven't really used it very frequently for other cases, except for in cases when we don't want threads interfering with each other, right? And you definitely do not want to pin a thread to core 0. So that's simply because the thread scheduler is going to be there, and if you get long-running threads on the core, in other words, it's going to use its time quantum, then your thread scheduler will just simply become less responsive because it just can't get into the core.
Okay, so yeah, great. Yeah, that's exactly what I experienced from using the task set. So one more thing, just to clarify. So with the task set of pinning to the core, the intention, or one of the intention, is to exactly what you just presented, to try to avoid context switching, right? You want to ensure that the specific process will be running on a specified core, so you can take all the cache lines related to that, and I think that's a huge improvement.
Yeah. So you can't prevent context switching. Context switching is going to happen. That's just how things work.
Between the cores?
But what you're affecting is the assignment in which task queue the task will be assigned to.
Okay. Yes, I agree. Yeah.
Right. So you will be context switched.
Okay.
You'll be context switched out, but then it's very likely you'll be context switched back. You'll be context switched back into the same core.
Right. Yeah.
Almost
right. Okay. Yeah. Makes sense. Yeah. Okay. Yeah.
Okay.
Right,
but there's a few misnomers. Like people think like, oh, if I have more threads, I have more context switching, and no, that's not the case. The context switching happens, and it's irregardless of the number of threads. It's just now you have more threads competing for those finite number of time quantums.
Actually, that's a good point. Yeah, thanks for the clarification. Yeah, all right, thanks.
Okay, no worries. It's an easy thought to slip into.
Does anyone else have questions? How come seems like a quiet?
Yeah, it's a quiet group tonight.
Yeah. I don't know whether it's because summer has just started.
Well, I was surprised to see this many people showing up, actually, given that it's summer, it's nice weather, you're in Chicago. I mean, your Chicago winters.
That's so true. Yes.
That's very true. Yeah. I guess I have a question for the audience. Are any of you seeing this problem? Is this resonating with you at all?
Yes, I can relate to that. Yeah. Mm-hmm.
Okay, that's one. I'm going to start picking on people. I don't know. No, I shouldn't do that. That's mean. I'll call you out. Although Stephen was around before.
Yeah, that's right. Where's Stephen? I'm expecting Stephen to be asking questions.
I was expecting it too, actually.
Most of the time that I have issues with concurrency, it's been I bring out Visual VM, and most of the time it's the garbage collection that just like pops up and down. And you just have to watch that and then try to trace down what kind of data structures are going through and narrow down what section of code that you're having issues with. But
yeah,
that's where I've had issues.
I gave up on memory too easily, I think, because there's still you still see a lot of it. But the funny thing is, like with the hyperactivation of the garbage collector, we always find that has to do with allocation rates and burn rates, right? and people misconfiguring the collector for their particular allocation rate? I don't know if you've seen any of that, Stephen.
I think a lot of the code that I've seen is that they're just memory leaks, where big sections of memory just weren't let go, and it's just patterns that people have gone and like they're carrying a large byte buffer in the stack, and then just trying to chain methods on top of each other without releasing the byte buffer. So.
Yeah, byte buffer. So it's like native memory leak then, or something.
I think this was actually a safe structure, and that they just kept it in the stack, and then one method was called within that method, and then it kept going down like that, so it kept carrying it over. I'm trying to think of some of the other issues that I've found. Most of it's memory. Most of the time it's you use a better framework, and then you don't run into these issues as much like Akka, where something gets caught up and then it's waiting to pass it down to the next one. Other than that, I can't say I've had too many issues with other systems.
And with the context switching issues or revolving. Okay, well that's it, and again it might be just the nature of the systems that you're working with. Like we tend to see this with microservices simply because people take the micro too literally.
Yeah.
And
I would imagine you'd run into issues, especially with memory on the serialization going back and forth. And
yeah, you do, and you can, but for these small ones, it actually takes a while to add up. And what I see is that people can actually configure their way sort of out of that problem, in the sense that they can get the garbage collector out of the way, but they're still taking the hit on the allocation. And as you probably know, that every allocation is a cache miss, which is it's a minimally 90 clock hit. Right. So you end up just basically run stall.
Yeah. One question I have for you is that have you ever had any or been able to solve any performance issues where you had to interline the data structures and the stream processing you had to do to the architecture of the system better, or how does that work out on VMs, especially when you get new processor types out there?
Oh, yeah, that's a good question. Yeah, unfortunately in Java, we still don't have the ability to control layouts as much as we would like. But I would say that, one of the projects I worked on with John Davies, I don't know if you might know him, where we actually achieved some really amazing results. We got, they were doing FPML, floating financial product markup language type things, right? Matching. And we were working at 25 million transactions per second. The way we did that was actually we did exactly what you're saying. It's like we used arrays to control the alignment of the data structures. And I think by doing that, we actually managed to get some caching advantages, because it's simply we're able to get the prefetchers fired up very efficiently in that case. So that's one case where we actually did manipulate the data structures to try to match our architecture. But that tends to work across all Intel processors. Of course, now everybody's interested in ARM, and I don't have an ARM system. Haven't played with an ARM system yet, although our group is working on porting to ARM. Matter of fact, one of my colleagues is here. She's working on part of the port here. And sorry? Yeah.
Hi.
Hi, Reka. So she's here. Yeah. So so she can talk about ARM architecture, maybe, I don't know. But so far I haven't seen anything in the recent version ARM chips that would cause me to change anything.
Okay. And okay. We have a question from Mark Johnson.
Okay. Is that it?
that-
Oh, that's in the chat thing, right?
In the
I should-
chat, yeah. So I can read
Okay,
too.
so where's the chat?
Yeah. Would you like to ask, Mark, or would you like me to ask? I guess I can ask too.
Okay, where's the chat? I should bring the chat open up.
No problem. I'll read it to you. Would the use of Docker increase the issues you talked about?
Would the use of Docker increase the issues you talk about? Yeah, well, Docker is effectively hypervisor. So yeah, that actually you'll take a hit because of that extra layer. Now, I mean, it's gotten better over the last couple of years, so the hits are much, much smaller. But I would say that yeah, you're going to get a hit when you run this in Docker. Absolutely. Oh, and here's one from Stephen here. Get Cliff Click and Charlie Hunt in the same room to face off.
Oh, let's just go back.
I don't know. Cliff and Charlie in the same room. That seems kind of scary.
That's fun.
Yeah, we've had Cliff in the room with other interesting people, and actually with Charlie, but at J-Crete, but yeah, Cliff is a regular at J-Crete. We haven't managed to get Charlie out there yet. Yeah, it's generally been interesting, I'll say that.
I would strongly recommend his talks. The one he did in 2019 was really good. I think it was on emotional intelligence and being an engineer, or it was introverts and engineers.
Yeah, that's yeah, that was an interesting path of discovery, and yeah, I'd highly recommend it. He did a couple of preliminary things at J-Crete before he actually went and created a talk out of that. So we've had some unconference sessions on that particular subject at J-Crete, which was quite interesting. It turned out to be not so kid-friendly, even though there were lots of kids running around the room. So that was fun also. So, I mean, if any of you don't know much about J-Crete, we actually encourage whole family participation in the conference. So we do have kids and spouses and other partners and stuff like that running around.
Could you?
The conference.
There might be some people here that are unfamiliar with the unconference stuff. Could you do like a quick elevator pitch about it?
Yeah, well, so we created J-Crete in the spirit of everyone is a speaker, so that when we go into sessions, you don't really have presentations. Well, we have rooms for projectors and slides. There's a couple of rooms, but we've been able to run like effectively 9 tracks for 3 times a day, where people come in, we set up the topics that we want to talk about, we get them all scheduled, and then people go off into different rooms and they have discussions, and generally we're supposed to come back and capture artifacts so that we can put everything together, and so that other people can benefit from the talks or whatever. That sometimes doesn't happen quite as nicely as we would like it, but you know. But generally in the session, we have a couple of different formats, but we just have a moderator, and then we have discussions about particular topics. Like, yeah, so one of my VinCat inspired talks was about fork join, and well, more importantly, the splitterator parallel stream topics, right? You know, should you parallelize your streams? And that VinCat was recommending. And yeah, so, you know, pretty much everybody in the room was very highly expert in the particular subject. So it was just, let's seed it and seed the discussion, and then just let everyone have a free-for-all in terms of coming up with ideas. So in that environment, you know, we just have these like discussion groups about topics of interest. And in this case, Cliff came in and said, hey, I have this other idea. Instead of talking about hotspot and compilers, let's talk about some of this softer stuff, which was quite interesting. And we've actually had physiotherapists involved, so they'll come in and we had discussions about office ergonomics and weird things like that. Or we've had people's spouses who were psychologists, so they offered all kinds of different sessions like that. So, and we do kids in programming sessions also. So where we have kids programming. So it's kind of a more of a family-friendly environment, I would suggest. And generally it's like sessions in the morning and the afternoon. We have get-togethers where people can do hacking or other things. And that sums up Jcrete in a nutshell. That model has been now cloned into Japan, in Scotland, in France, in Germany, and yeah, in a number of different places.
Is it like a week long or?
Yeah, we go 4 days of conference, 1 day of hack, and 2 days kids.
Okay. Cool. Very
Yeah.
cool.
So that's a derivative of the DevOps for Kids program.
Some of the others like JABA, and that's the famous one, and I think JSpirit, that's in German.
Yeah.
Those are like weekend long, and that's, if we want to do that in Chicago, I'd certainly suggest kind of dipping our toe in that way.
Yeah. So yeah, Maurice runs JALBA, I should say, in Edinburgh. So he's actually done it online this year, and Sebastian Dashner runs JSpirit. We also have J Chateau in Paris that's run by some people from the Paris Jug also, and Jay Onsen was set up by Stephen Chin, which is, I guess he's J Frog, right? So I don't know if we have Stephen coming in, or I don't know who's coming in when you said you had J Frog coming in.
Oh yeah, JFrog. Yes, JFrog is our sponsor. So yeah,
Yes.
Ari will be here. So
yeah, so who's coming in?
Ari.
Oh, Ari. Okay, so Ari's coming in. Yeah. Okay, that's interesting.
He normally comes as the community manager, so he would come. So
yeah, so Jay Onsen was an interesting setup. We set that up about 4 years ago now, 5, 4, yeah, yeah,
and
yeah, we combined that with a whole let's go visit Jugs in Japan tour.
Oh.
So it turned out to be more like a month-long event, road trip.
Oh.
So yeah, it's kind of fun. Well, you know, Stephen, right? So go big or go home, right?
Yeah. Yeah, Stephen Chin. Yes.
Yeah, pretty much it.
I think Chris Tellinger, he runs the one in Hawaii, right? Unvox.
Yeah, actually, yeah. So we had Chris Tellinger to come to Jcrete, and that's where we got him all gussied up on unconferences because he wanted to run a full conference, but we didn't think he was going to be able to pull that off.
Oh.
Right. That way. So we said, run an unconference will be a much better experience. So I convinced him to run an unconference in Hawaii. So he used the Jcrete model there also.
Oh, got it. Yeah.
Yeah. So yeah, that's right. I'd forgotten about that one. Yeah. So yeah, so I think people are really looking forward to having that one restart. It's in February. So good time to go to Hawaii, I guess.
Especially for people in Chicago. So
yeah, especially for
yes, that's very cold.
Yeah, absolutely.
Yeah.
Right.
Yeah.
Okay. Well, okay. So that's like
I have another one if you don't mind.
No worries, Matt. Yeah, fire away.
Yeah, thank you, because I wanted just to take advantage of having you here. So somebody mentioned byte buffer. I think that's quite an interesting question and important topic because it's not well known. And my question is, what are the good cases and the things to watch out for when allocation is either direct or indirect? So because you can allocate a byte buffer indirectly and directly, they are both about cases, but every case has its own specifics. So can you explain what's the consequences of each of them? Indirect allocation and direct allocation, right?
Direct, indirect. Okay, so
right.
Okay, so I'm going to assume a definition of direct and indirect. So it's like being, you can tell me if I got this wrong. Direct being I'm typing new byte thing in my code, as indirect means that it's happening magically under the hood as part of me setting something up. Is that what you're saying?
That's a good question. I refresh my memory, and I think when you allocate a byte buffer with just to allocate, you in a heap. But if you call the API, I don't remember, I think that there's something with direct, allocate direct. That means that you can allocate on systems outside of JVM.
Oh, okay. So
the allocation, direct allocation will take longer, but then it's faster, right? Because you're talking directly to the OS layer, right? But then it's outside of the JVM, it won't be garbage collected, right? So there are trades-offs. I'm just curious, what was your experience? What to do in each cases? A little bit about, yeah. Mm-hmm.
Okay, so I get what you're saying. So you're talking about on heap and off heap allocation then of the byte buffer.
With the byte buffer, yes, that's what it means with allocation, to my knowledge at least. Correct me if I'm wrong.
Yeah. So so there's very few things that will actually do an off heap allocation of a byte buffer. I mean, you can do it, but it's so like zip does it as an example by default. Now. So the thing is, like with the off heap, you need to be really careful because you need to manage the memory yourself, and if you forget or the thing that's created the byte buffer, like this was a problem with zip, but I think they've cleaned it up with cleaners or finalization now, so that when if you don't properly close down things, then that byte buffer remains allocated and it will never be garbage collected. And what happens is that your process size gets bigger and bigger and bigger as you allocate more of these. Eventually you spill swap. You take a performance hit when you spill swap. And then if you keep doing it, eventually you'll just run out of system memory and you'll hard crash because of that. But the real cliff event is when you run out of swap space. So you'll see some degradation, then you hit the cliff, and then off the cliff you go. So that's pretty much the only story I can say about the off heap allocation. The on heap allocation is a little different story, and that really gets tied into the type of garbage collector that you're using and how big the allocation is. So as you know, the garbage, Java heaps get subdivided into a number of different buffers. And depending upon the size of the buffers and the size of the byte buffer that you're trying to allocate, it will force the allocation either onto good slow paths or onto a fast path or possibly onto slow path. The worst cases, I think, slow path allocation in tenured direct is going to be like 10x slower than an allocation in young gen. And even there, it comes with the issues, right? So that's for like generational collectors. So if you get into quasi-generational collectors with like G1, then you have to worry about region sizes because that gets into humongous allocations, which are still basically a pain in the neck for the garbage collectors to manage. They've gotten much better at it, but it's still extra work for them to muck around with them, and you get a lot of copying and stuff like that. With ZGC and Shenandoah, I honestly don't know the answer. I don't have enough experience with those collectors yet to claim what they will do or won't do with these things. I mean, ZGC will have a large page space, which hopefully they fit into, so you don't have to get into a general heap allocation situation, because I imagine that's going to be more expensive, right?
Yeah, okay.
Or you're going to have to like stack up pages, right, in order to do the allocations. The same with G1. You have to stack up regions in order to perform the allocation. And if you have a highly fragmented heap, then of course that's you have to defrag and before you can perform the allocation. So, the issues just, these large allocations, they just come with a number of issues. And generally, what we'd like to do is that if you have these large allocations, especially for buffers, is that try to allocate them in a way that you can reuse them so that you don't have to keep reallocating them. A lot of the frameworks that you use, like especially the JSON marshalling, unmarshalling frameworks, don't actually do this. They'll allocate and throw away, right? And
I think you mentioned Netty, right? Netty uses a lot of byte buffers. They own actually versions.
Yeah.
And I'm not sure about, they probably do a lot of direct buffer allocation, but anyway, that's the right point. Oh.
Yeah, I think they do. I have to go back and look to remind myself. I haven't looked at it for like ages. Yeah, but in that case, I think Netty actually pools them. So these byte buffers get reused.
Oh, definitely, yeah. Definitely.
Yeah. So, but that's the exception. That's not the rule.
Yeah. They have a nice counter to even count how many. Yeah, that's fine. Yeah. Okay. Cool. Yeah. Thank you.
Mm-hmm. Yeah. But yeah, basically, large allocations can be painful in the JVM. So you want to try to minimize them. This is a great question. Thanks.
I guess let me ask you again, Kirk, because I know you and I we talk a bit too about like in today's world, right? Cloud native, we're talking about microservices, and as you mentioned too, if we take microservices and implement it the way like the true kind of pure microservices, then actually we will run into problems that you are describing with performance. But so in today's day and age, what would the recommendations be like, right? If we're going to be using microservices, how should we do it so then we don't run into problems like with the thread scheduler? Do you have any recommendation?
Well, I think that it's a really good question, and I had just recently read something which was a really good answer to it, and the details of this whole thing are just sort of, so I have to go back and look it up again. But the essence of the message was that we need to design microservices upon that are the way the author of this particular posting put it perfectly, and I'm going to mangle it, but here it goes. We need to actually have true separation in the service. And so taking a monolith and actually breaking it up doesn't really give us true separation. We still have dependencies there. And these dependencies might not be compile time dependencies. In other words, they might be implicit dependencies as opposed to explicit dependencies. But if we have these type of dependencies, then I guess, he described it as testable units. So a microservice should be testable on its own. If I need other things or other microservices up in order to test, then I probably don't have a true microservice. Okay. And I think when you get into that definition, what happens is you naturally start bulking up the microservice. So it's no longer micro or too small. So that means the incoming threads are actually going to do significant amounts of work, or enough work that that they're going to be out and gone and doing something for a long enough period of time that you're basically not churning through threads at a horrendous rate. And really what they're saying is like, I need to bulk up the work, right? And I think if we truly design a microservice properly, then we naturally get that bulking to happen.
Okay, makes sense. Yeah. Okay.
I don't know if that answers the question, but
yeah, it does. Yeah, but also means maybe when we're doing design on application level, we really have to start thinking about it in terms of how does it handle all of the threads underneath the hood and all these kind of things too. So it just requires more thoughts to plan.
Yeah, that's absolutely the case. I think you need to understand where the barriers are, where the expensive barriers are, and just make sure that when you cross them, it's purposeful,
That's right.
so that you understand that is an expense. That call's not free. It's you're going to take a hit, and if you're on the network and it's a millisecond, that's what you can generally count on. I'm gone for a millisecond.
That's right.
So that's, it might be quicker than that, but generally, rule of thumb.
Okay.
Are there any performance tips that you would give for data pipeline type systems rather than outside the microservice architecture? Typically, like Kafka or those related types of pipelines.
Great question. No, in general, I like the way that these things flow, and how in general how they work. These are like high performance systems. I think you just want to try to understand them and not get in their way.
Mhm.
Is the biggest thing, right? If you don't get in their way, they will perform very well. And I think like the push models are like the React type models, where the data is being pushed through the system as well as instead of being pulled through the system offers some huge advantages. It allows you to implement eventing, and in my experience of event-based systems are generally the most performant and the highest have the most ability to scale. They'll scale much farther than other types of systems.
Mhm.
So yeah. So if you look at our our garbage collection analysis tooling, you might think, oh, it's just like we're going to read logs and splash data on it in charts on a screen and everything like that. But the engine that we're working to open source right now is all event driven, and it's all push. Right. So right from the data coming out of the file right through the entire system. It's all flowing in one direction, and really the dependency across the system are the events. So everything else is fairly loosely coupled.
So I think something like Akka like messaging or Vertex.
Yeah. Akka. Yeah, very good. We actually are using Vertexes on the core of
Yeah.
of our application, Sensum, and it's a high performant messaging backplane. There's, I guess, Martin Thompson wrote another one.
Disruptor.
Yeah.
Disruptor from LMAX. Yeah. I was just about to ask you this.
Yeah.
What's your opinion on this framework? Yeah.
It's a completely game-changing, brilliant framework.
Okay.
Right.
Yeah.
So that's the way that he's architected and the way he's built observability into the whole thing, and just all of the different it's a work of genius, right? And their messaging product that's built on it again. And you have to look at some other projects that are built that way. It's like Peter Lowry's Chronicle.
That's right. Yes.
It's sort of built in the same style. And again, it's like, don't get in its way, and it performs at the speed of hardware.
Right. And as you mentioned, single threaded, right? You can get a lot of you can get a lot of things in one single thread done fast and in the correct way. Yeah. Okay. Yeah.
If you're going to transfer data between threads, you have to consider that the transfer of the data between threads is effectively a context switch. And a context switch is, Charlie Hunt has estimated a context switch to be about 80,000 clocks. So now you have to think, it's like, how much work can I get done in 80,000 clocks? Right? And generally that's quite a bit.
Interesting. Yeah, that's good.
So now the question is it worth it for me to pass this off to another thread or just take this on myself?
Okay. Yeah. Thanks.
And I guess the other thing, the fun thing we had, I guess, and I guess the engagement in Chicago when it came to this event single-threaded systems, your responsiveness is now down to how idle can you make your event thread, right? So the more idle your event thread is, the more responsive your system is going to be, and this becomes a really simple problem now. It's just like punt instructions out of the event thread. That's all we want to do, is we just want to make sure the event thread, the number of instructions it's executing, is as small as possible. And and there's different techniques that we've used to do that, and a lot of that is just slicing out extra work, and sometimes that's creating an extra event.
Yeah.
One of the questions I forgot to ask you is, are there any particular tools that you recommend for performance analysis, like UKit or and I think there's Plumber and such? Do those actually help, or do they get in the way?
Yeah, that's a loaded question. uh, mostly I use just low-level tools and very raw tools. I don't have any tool preference that way. As you can see, I was using VMstat, and that was pretty much the only tool I've used in that engagement was VMstat. And that was good enough to figure out what we needed to figure out to move forward. Oh, sorry, I used Sensum, obviously, which is our GC analysis tool. In that case, also to understand the memory requirements of the application. But I think the biggest thing I use is my performance diagnostic model, right? And so like that magic 10% number I gave you as part of the presentation is an approximation of the number. Well, it's not imperative. Also, it shifts around. So we actually use AI framework in a product called Illuminate that helps us do the diagnostic work. So that'd be my preferred tool. If I can't get it in, then I'll just do that by hand. Right. So it means I have a number of magic numbers, and I'll just look at the hardware counters and the garbage collection statistics and throw that in a mix, and then make a decision from there as to what to do next. So yeah, your kit, perfectly good tool. Nothing wrong with it. JProfiler, nothing wrong. I mean, the tools are just fine. It's not really the tool. It's when and how you decide to use it is the issue.
Have you tried anything with the BPF framework that Brandon Greggs tends to promote?
I actually haven't used anything with his particular framework, but I do. The one thing, okay, so the one thing I like to do in all of this is, or one thing I've done in all of this is I've tried to come up with some taxonomy for basically classifying performance issues, and what I found is that once I've done that, it added a lot of structure to the performance tuning or performance diagnostic space, and it's basically given me a framework to do a number of things that I don't think would be possible without having this sort of classification mechanism available to me. And I think the one other person that I see that's actually published a lot of similar ideas in terms of coming up with some form of taxonomy, although his is fairly different than mine, and it's just as good, maybe it's even better. The things he's done is quite amazing, but Brandon Gregg is actually, what he's done is he's added structure to the problem, and he's done this by coming up with some form of taxonomy or some way of classifying the issues, so that when he looks at an issue and he looks at the state of the system, he says, I know immediately now what tools I need to use in order to best visualize this particular issue so that I can fully understand it, right? And so that's really using Brandon Gregg's use methodology. Yeah, and he keeps evolving that over time. So I use what I call JPDM, and he uses use, but they achieve the same effect. What they do is they apply some ability to do some categorization, which helps us, understand the problem and then understand the tool sets that we need in order to further characterize things. And that's really the brilliant thing that he's brought to the table, in my opinion.
What is the Microsoft attitude towards Java in terms of, are they thinking getting into Java more seriously? Like they bought your jClarity, right?
Yeah.
Coming up with the tools, etc. Because I think when you think Microsoft, you don't think Java, right?
Yeah.
Most of the time. So I'm just curious. Did they change their attitude? Yeah.
Well, no, it's okay. So I think what they started off with doing with Azure is, they looked at it and they said, okay, well, a lot of our customers are also running Java workloads, and so initially they went out to Azure and they said, okay, well, can you do something for us here? And so they made this. So they had this contract with Azul that's still there today. And so why did they buy jQuery? Well, there's a number of reasons. That one, they wanted to send a message that they're serious about Java. They're serious about supporting Java in Azure. They wanted us to come up with our own internal build of Java, which we have today, which means that and we have our own engineers, like Reika was here. So she's doing the port of the JVM to ARM, but she's also involved in helping ship the Intel versions of the JVM, and we have a small team of engineers that are busy beavering away, looking at issues that are cropping up that are unique to Microsoft. So we are fixing them, and our intention, as I understand it today, and it's a position that I certainly support strongly, is that we are upstreaming all of our fixes. So when we find an issue with the JVM or it's reported, we're going to fix it and we're going to upstream the solution to the issue. So like once a week, I run what I call a bag of bugs session, and that's what we do. Is we just look at OpenJDK bugs or bugs that are coming up in our test environments that we've set up, and we're fixing them. And
Wow, that's interesting.
Upstream them.
Okay. Oh, okay.
So, yes, Microsoft recognizes that that Java is an equal partner to anything else they're supporting on their platforms, and they support Python or a whole bunch of different runtimes, I guess. Spring Boot is a huge deal for Microsoft, and there's lots of services that
Didn't realize that. Okay. Mm-hmm.
We own LinkedIn. Microsoft owns LinkedIn. LinkedIn is almost it's at least 80% Java, if not more.
Right. Yeah. Oh.
So that's one of the customers that we support today.
Okay, thanks.
Very serious.
No questions?
No, I think we might be, well, it's getting late, I guess, for you guys. It's like 9 o'clock, so.
For us, yeah.
Yeah, I can imagine.
Yeah,
great presentation. I really enjoyed it for the simplicity of it. Straight to the point, exactly to avoid revolving doors pattern. Don't get into some convoluted talk. Just do less as possible in thread and get out of it. Yeah.
Yeah,
thanks.
Yeah, well, thank you very much, Matt, for your kind words there. And so I think I enjoyed the opportunity, Mary, so thanks for the invite.
Thank you.
And
Thank you, Kirk.
if you want a memory talk, I'm happy to go do an old boring memory talk in the future with you guys. But I'm looking forward to the day when we can all get together. I don't know.
Yeah,
we'll see.
That would be great. Yeah. Actually, Stephen and I are thinking of, we like to do an unconference in Chicago. Maybe we'll have you as our honored organizer, program committee or something.
Well, sure. I mean, I'm very happy to share our jQuery experience with anyone who wants to set things up.
Sure. Yeah.
So,
I think the basic, we were talking a little bit in the side channel, but I think the basis of that is keep it short and keep it sweet for starting out. So kind of like the JAlba type of approach, but still at a time where you can do outdoor events and excursions. Yeah.
Yeah.
I think that Maurice set that one up brilliantly. So it's a well accepted event. JSpirit, same thing.
Okay.
Yeah, although having having a conference in a distillery, it sort of seems somewhat counterproductive, but that's the way it is.
Yeah, that's one of the things I was hoping
That's funny.
in the unconscious stuff is that it's not intended to be like you have to be constantly professional and like on like mental awareness every single second. So
yeah, and we find that environment actually opens people up to different possibilities and different types of they feel safer in those environments, and because of that, the interactions are very, very different. I think Heinz summarized it very nicely. He says that at a conference, you pretend to work when you're there to play, and he said we're pretending to play when we're actually doing a lot of work.
That's a good one.
Yeah, I like that. But you think of it's really kind of flattering when I think of the influence that the conference has actually had on different things. Like if you look at the people that we've had there, we've had a number of things going to the JVM simply because we had JitWatch come out of that, and there's a whole bunch of different collaborations and different projects that have basically sprung out of there, and we've catapulted people's careers. I think JFrog, Melissa McKay is one example of it, but it's not just her, it's her daughter. Her daughter started participating when she was 15 years old. When she was 17, she held an unconference at her school based on jQuery.
Also, Steve Chen, and when I was there, it was Steve Chen brought in, I think Laurie, and also Melissa to Jake for that reason.
Well, Melissa was brought in beforehand, but Laurie was brought in, and we managed to help her help Chris with the Hawaiian conference.
Oh.
So we got her to actually be the MC in that case. Well, she was trying to anyways, but I'm not sure how that all worked out. I mean, it worked out well, but it was anyways.
Yeah. Yeah.
But yeah, so I think these create great networking opportunities, and they create great opportunities for learning, and it's we've had people leave the conference and effectively start their own business. They said, this has given me enough confidence to go and do something interesting.
Oh.
So
that's very good. Yeah.
No, so it's a flattering position to be in, I think. Yeah. To know that we've managed to have. Well, I mean, Heinz and I wanted to try to create an environment where we could have a positive effect on people, and I think that's exactly what we've achieved our goal, and that's very satisfying.
Oh, that's cool. Yeah.
Yeah.
Yeah. And I like the idea. Yeah, we've just started like smaller, kind of cozier, and a lot more interpersonal type of interaction, right? So
we started with 35 people, I think, our first one.
Oh.
And now our last one was like 150 some odd people.
Okay.
And we were actually only aiming for 100.
Oh, okay.
So it just somehow grew a little bit but we expect some out of proportion growth, but we were really trying to keep it to around 120.
Okay.
Even at 120, we've had to make several adjustments to be able to cope with that many people with that style of conference.
That I think when that year, I think that it was pushing the limits of what the town could actually hold and to reasonably get the logistics working out for the conference. The venue was a problem, but yeah.
So Columbari, so having in Columbari does place certain limitations in terms of infrastructure, but I think it placed a lot of challenges on the organizers. They're the disorganizers, as we call them, in terms of so in Crete we don't have meetups, we have swim ups, which means that you swim out in the middle of the sea and then you get in a circle and you have conversation, right? So we actually had to have a swim up before the conference, and I basically said, if you do the numbers and you look at what's going on, we're never going to be able to hold a proper marketplace, right? In other words, we as disorganizers need to get out of the way in order to have to be able to get through these tasks in a reasonable amount of time. And so it's quite amazing to step back and watch the process, because it's incredibly chaotic. But it's interestingly chaotic in a sense that everybody is working towards the same goal. And all of a sudden, out of all the chaos, things go from the launch board, they get matched up and they get on the schedule and everything like that. And everything just sort of crystallizes, and it just sort of like comes together, like it converges very quickly. And it's quite amazing to watch, because there's no one in control of any of the process. So the level of chaos is just absolutely astounding.
Wow.
I don't know if you noticed that, Stephen. Like on day one, it just looks like a mess, right?
Yeah, it's a mess. My experience was a little bit different because I got approval to go over and to do that without taking vacation days much later. So I was staying in a place about a mile away from it, and it took me about like 20 minutes to walk there every day. That's a little bit of a difference there. It's a compliment and a complaint at the same time, is that some of the activities, there wasn't really structured activities.
No.
Way like, we're going to this beach or that beach.
No.
There's a lot of options that people come up with, so you do have alternatives, but sometimes a little bit of structure to say, like, this is our recommended event. I guess kind of the beach was a recommended.
We had that. We had recommended events.
Yeah.
Yeah. Maybe you missed it. Yeah. But if you didn't show up to the sessions where the in-between sessions, you would have missed it.
Yeah.
And also with the unconferences, like, if you saw a problem, fix it.
Yeah.
Because everybody owns the conference. It's not ours. It's everyone's. It's what you make of it.
Well, I mean, I'm just saying, it was, for me being new, it was just kind of hard to find out, like, what are my options here? And it's kind of hard to say, yeah, I'm going to commit to the scuba diving thing, and then you don't know what the other options are. So.
Yeah, that part is chaotic also. I do agree with you on that point. So, absolutely. But I think it's, people were saying like, oh, we don't like the coffee. We said, well, okay, well, you want to deal with coffee, and they'll pick it up and they'll do it. I mean, I used to help organize swag and things like that, but somebody decided they wanted to do it, and I'm going,
yeah. I can't imagine anybody complaining about the coffee, because that was one of the things of, you go down to the grocery store and get somebody with a car and just load the back up with beer. That's kind of what we did.
Yeah, that's pretty much what happens. I mean, so for those of you who haven't been there, there's an incredible amount of sharing going on. In other words, that we set up a spreadsheet, so some people will rent cars, and other people just piggyback in, and so there's a lot of sharing and things like that happening, which can lead to some confusion also, I guess, because if you're going to one of these things and you don't have a car, then you really need to find the person with the keys and stick close by. You know what I mean? Yeah.
Does Uber exist?
Sorry?
Does Uber exist?
No.
No.
Greece, it does not.
No, especially not there. They do have taxis, but all the taxis have to come from the airport, which is about an hour away.
Oh my.
So, yeah, so it's kind of fun.
Wow.
But, I mean, you can schedule them, and they work very well, but there's not an issue. But, yeah, if you do it randomly, then, yeah, you could be waiting. It's a high latency. If you don't do it predictably, it's high latency.
I believe it's Greece and it's Italy that they're strong against Uber. So Italy tries to do scheduled taxis by Uber.
Oh.
Uber tries to do that. And then Greece just completely does not.
Oh.
No.
Or at least it doesn't do that in Crete. I think you can do taxis in Greece. I'm not sure.
No, taxis were invented in Italy, weren't they?
Oh, they
like
really?
the meter. Well, the meter taxi is a Roman invention.
Oh, I didn't know. Huh.
Yeah. They put prongs on the sides of the wheel so they could have some counter to count how many times the wheel clicked over. And they would charge you based on that.
Wow.
What's worse, that or your AWS bill?
I guess so, yeah. That's really funny.
Oh,
Okay.
yeah.
Yeah, it's an experience, I guess.
Cool.
It's quite fun.
Very cool.
But yeah, so yeah, I recommend, Mary. You need to add something to your pile of things to do. So
I was gonna say that's right. Yes, it's already enough. But that's something I've been wanting to do too. So I know Stephen's interested. And I said, well, maybe we can do something. Yeah, put together something. Yeah, something small to start with. Maybe good.
right. Yeah, I think so. That's quite fun.
Find some sort of a theme in Chicago too. That would be good as activities, right? As you said, maybe something.
Well, we tend to, like, we have a couple of suggestions on the board, but if people want to do other things, then they're, free to do so. But the point is that getting people out into an activity generally means that people are together and they're having the interesting discussions about different things. So you basically, it encourages, quote unquote, the hallway conversations. And we find the hallway conversations are, the sessions will prompt things, but the hallway conversations are where things really happen.
Oh, okay. Very interesting.
Yeah. So that's why we focus in that direction.
Oh, okay.
Yeah.
So,
Like I said, yeah, we pretend to play when we're actually working.
Yeah, the best conversations I had were, it's structured this particular way is that you do about 3 different talks. You either host or you go to them. This time you're going to be going to them. And then they do like the beach trips. So you're talking about stuff after that. And then whenever people are talking about the beaches, it brings other people along. And also, you kind of find who has a car and kind of join them and figure out what's going on.
Yeah.
That's how it goes. And then you're in the ocean complaining about like security and Java and with guy. I can't remember that guy's name. Warner probably.
That's funny.
Yeah, Werner. Yeah, he's good at complaining.
Yes.
Miss him dearly. Okay.
Or Deutsche Bank or Bank.
Yeah. Exactly. That's really fun. Right.
Yeah.
Okay, guys. I think it's getting kind of late, and just for Mary's sanity, I think what I'll do is I'm going
No
to
problem.
to drop out and everything. And once again, it's great catching up with you guys, and
Thank you.
hopefully, Thank you so I think, given the list, I think I'll be attending some of the JUG events going forward. So
that'll be
amazing
wonderful.
list.
Yeah, please do.
Okay.
Yeah. Okay. Well, thank you, Kirk. Thank you so much
thank you,
again.
Mary. Okay.
Okay, thanks again. Yeah.
Okay.
Thanks.
Thank you, everyone, too. Yeah, thank you, everyone.
Right.
So,
Yeah,
okay.
thanks.
All right. Yeah.
Okay.
We'll be in touch.
Bye.
Okay. Bye-bye. Bye.